As of June 2006, there were 442 nuclear plants generating electricity in 30 countries, and 27 new ones under construction in 11 countries. Why is nuclear energy attractive? Nuclear energy also produces no carbon dioxide emissions and generates no air pollution. Much more energy per unit of weight for uranium, and very much less material to handle. For example, to produce 1,000 megawatts of electricity for 1 year requires 3.8 million tons of coal. For a simple comparison, let's assume that this amount of coal represents the entire surface area of planet Earth. It would require only 160 tons of uranium using the current thermal reactors to generate the same amount of energy. Compared to the surface of the Earth, this would be roughly twice the size of New York City. Furthermore, it would require a mere 1.6 tons of uranium using the 100 times more fuel-efficient fast reactors. Compared to the surface of the Earth, this represents a city roughly the size of Ithaca, New York. This comparison shows why countries with little or no coal resources find nuclear power very attractive. Nuclear grew rapidly from 1970 to 1995. Since then, however, growth has slowed significantly. World electricity consumption has more than tripled since 1970. The growth rate of world electricity consumption has declined only marginally over the period. The Energy Information Administration expects world electricity demand to grow by 57% to 79 exajoules per year by 2020. It is difficult to believe that nuclear will not grow again as it did during the period 1970 to 1995. For the purposes of this analysis, renewable energies are generously forecast to maintain the current ratio of about 9% of world energy demand from today through to 2100. During the same period, the world's future energy consumption may well more than triple. The gap or shortfall between what is required and the contribution of renewable energies is about 1,300 exajoules. This gap is about 3 times current world primary energy consumption. By 2100, oil and natural gas will be scarce, no longer abundant and affordable, and the easiest and best coal will have been mined. Renewable energies are often portrayed as the solution to energy supply and climate change, but your research seems to contradict this.
Yes. Although renewable energies attract a lot of attention, they are, in fact, now and in the future, very small contributors to world energy demand. The scale on which they can be used falls far short of replacing the 388 exajoules of fossil fuels used in 2005. The gap between renewable energy supply and possible world energy required in 2100 is large and very real. Oil and natural gas will no longer be abundant and affordable well before 2100. It appears that coal will last for 1 to 2 centuries. We have seen that energy conservation has a small effect and would reduce the gap slightly. Energy efficiency increases are physically constrained, and the 1% average annual reduction in energy per unit of output is not likely to be sustained, thereby increasing the gap. Now, the problem can be accurately identified.
That being?
In short, energy must be found to replace fossil fuels on the scale required to fill the gap between the contribution of renewable energies and world primary energy today and in 2100. Otherwise, income per person will begin to slide, and the well-being of everyone and the environment will suffer.
We need more energy. Energy supply is far more important than climate change. It may also become a crisis in the not-too-distant future. We need sufficient energy to adapt to climate change, whatever the cause may be now or in the future. We need sufficient energy if we are to protect the environment, Otherwise, it will be destroyed as, for example, in poor regions where every tree has been burned for fuel. The crucial question is, where or how can we obtain more energy? There are only two sources of primary energy available to us on Earth: nuclear fusion, which is combining of atomic nuclei, and nuclear fission, which is splitting atomic nuclei. Relatively small amounts of energy are available from hydroelectricity, which results from the Earth's gravity forcing water collected behind a dam through hydraulic turbines; geothermal energy, which results from radioactive decay of elements in the center of the Earth that keep it warm. Hot spots in the Earth's crust expose this energy where it can be exploited. Ocean tidal energy, which results from the Earth passing through the gravitational field of the Moon, can be used to generate a small amount of electricity. Nuclear fission is the only one of these sources that is here now and has sufficient capacity to replace fossil fuels on the scale required. Fusion reactors may one day provide heat for steam to generate electricity. However, experiments have been carried out for decades, and success is just as far away, several decades at best, and further away still to be deployed on a large enough scale. Nuclear fission requires fuel which is mined as uranium and/or thorium. Thermal reactors use uranium to produce heat. Heat from thermal nuclear reactors is used for generating steam to drive electric generators and provide electricity. Nuclear reactors are also used in specialized transportation applications, such as the propulsion systems of large ships and submarines. It was used to propel the New Horizons space probe recently sent to Pluto, once it was in space. Nuclear fission technology is well enough developed that its use can be expanded into residential, industrial, and commercial energy sectors, and possibly into other transportation applications. If all world energy today could be provided by nuclear power, there would be enough uranium for 10 to 30 years based on reserves at a price of $80 US per kilogram. Thermal reactors use only 0.7% of the energy in the uranium. The remainder is waste, and some is radioactive enough to be of concern for thousands of years. However, fast reactors use virtually all of the energy in the uranium and are 100 times more fuel efficient than thermal reactors. Replacing the thermal reactors with fast reactors would, therefore, increase the life of uranium reserves to 1,000 to 3,000 years. With reprocessing, existing waste from thermal reactors is fuel for fast reactors, and there is enough to supply all of the world's energy needs using fast reactors for more than 150 years. Fast breeder reactors are not new. The first nuclear electricity ever produced was by a fast reactor in the U.S. in 1951. A fast reactor has been delivering electricity in Russia since 1981, and another in France since 1974. Nuclear fusion powers the sun and provides the renewable energies which are far too small to replace fossil fuels. The supply of coal, oil, and natural gas, which accumulated over hundreds of millions of years, is limited. Oil shows signs of becoming scarce within a decade or two. Only nuclear fission using fast reactors has the capacity to replace fossil fuels. The key point is that nuclear fission using fast reactors must be made to work very well if the world is to have sufficient energy. There is just nothing else on the scale required, either now or in the foreseeable future. Safety of thermal reactors is proven. The design and operation of fast reactors involve similar procedures to those for thermal reactors. The small differences tend to favor fast reactors. Both types of nuclear reactors can grow because safety is under control. It is not an engineering problem. If this were not true, then 27 new nuclear generating plants would not be under construction as we speak. Proliferation possibilities are reduced by using metal fuel in fast reactors and electrochemical reprocessing in which plutonium is never pure but always mixed with other materials. The UN procedures for thermal reactors have been proven to work and are applicable to fast reactors. The neutrons in a thermal reactor are slowed by a moderator, such as carbon or water. Slowing the neutron increases the probability that a uranium-235 atom will fission and release energy when struck by the neutron. These slow neutrons cannot fission the uranium-238, which is 99.3% of naturally mined uranium. There is no moderator to slow neutrons in a fast reactor. The fast neutrons can convert uranium-238 into plutonium and fission the plutonium. Thus, they can use virtually all of the uranium as fuel, versus 0.7% for the thermal reactors. That is why fast reactors are 100 times more fuel efficient than thermal reactors. The waste from fast reactors is more easily managed because the fast neutrons split almost all of the long-lived nuclear waste products associated with thermal reactors. The radioactive materials remaining from fast reactors are of concern for less than 500 years, rather than thousands of years. If fast reactors have such a large fuel economy advantage over thermal reactors, why are there not more fast reactors in use today?
The answer has three parts. First, uranium has been so inexpensive that there was little incentive to use it more fuel efficiently. And the storage of unused uranium and other nuclear waste is manageable. Second, thermal reactors were the first to be introduced commercially and have been continually improved. So, thermal reactors have had a real head start. And third, up until recently, our fossil fuel energy supply was perceived to be secure. However, concern about secure energy supply is now generating renewed interest in developing modern, commercially available fast reactors. For example, in order to extend their nuclear energy resources, India, China, and Japan are investing in programs to develop advanced fast reactors. This is of particular interest to Japan because they have no indigenous uranium supply.
Can you tell us a little bit more about how fast breeder reactors work?
Uranium, as mined, has two kinds of uranium atoms. Some are radioactive and some are not. When a radioactive atom splits, it releases an atomic particle called a neutron and lots of energy. The design of thermal reactors slows the neutrons because the reactor works better that way. But the reactor can use only the radioactive portion, which is about 0.7% of the total. The design of a fast reactor retains the speed of the neutrons and uses them to convert all of the 99.3% of the remaining uranium into plutonium, all of which can be fissioned to release energy. Advanced fast neutron reactor technology uses metal fuel. The recycling process for metal fuel does not involve pure plutonium at any stage, thereby minimizing the risk that spent fuel from energy production would be used for weapons. At the same time, it squeezes the maximum energy out of the nuclear fuel.
But is there still an issue of waste from fast reactors?
This is an important difference between today's thermal reactors and fast breeder reactors. The waste from fast reactors is much less radioactive than that from thermal reactors and is of concern for less than 500 years rather than for thousands of years. Furthermore, existing nuclear waste from thermal reactors is a good fuel for fast breeder reactors. And there's enough on hand to power the world for 150 to 200 years.
There's a lot of controversy about nuclear energy. What do you think the average citizen should know about nuclear energy that they're not being told?
Nuclear fission is the only alternative energy source with the capacity to replace fossil fuels and deliver power when and where it is needed.